Satellites orbit around things. I mean, everybody knows that, right? But why don't they just crash into Earth? What's the physics behind them? Haven't we covered that objects with a big mass attract other objects in the last video? How about we do a little thought experiment real quick. Let's say we have a cannon on a hill. By firing the cannonball, it gets pulled towards Earth. And the higher the speed is, the further away the cannonball travels. Now satellites move fast. To be exact, 28,800 kilometers per hour, or 17,895.49 miles per hour in freedom units if a satellite moves in a low Earth orbit. Otherwise, it would crash. So the speed basically counteracts the gravity, or in other terms, the tangential velocity, or in other words, the rate at which a satellite moves around the edge of a circle, at any instant counteracts the centripetal force, the force which tries to pull the mass inwards in a circular system. If the tangential velocity would be too high, the satellite would fly away, and if it would be too low, it would just crash into Earth. When a satellite moves in uniform circular motion, the net centripetal force acting upon the satellite can be represented as the following. The centripetal force is equal to the mass of a satellite times its velocity squared over the radius. Since the centripetal force, the force which tries to pull the satellite inwards, is just gravity, which can be represented as the following, we can set both equations equal to each other. Since the radius and the mass of a satellite are on both sides, we can just cancel them and search for the velocity. Crazy. Satellites can also be geosynchronous, which means that they finish one revolution in 24 hours, just like Earth. They remain stationary towards Earth, and since they're so far away, they can cover 1/3 of Earth. To make a satellite geostationary, a satellite has to be at an altitude of roughly 35,000 kilometers, because that's the altitude where the gravitational force precisely provides the required centripetal acceleration, which is equal over v squared over the radius. You could also achieve this geosynchronous state at a lower altitude, however, in that case it would finish one revolution under 24 hours. So you would need to make them artificially slower by using thrust. But wait a minute, if they would travel too slow, then they would just crash into Earth, which is why you would also need another thrust engine that points towards Earth. So yeah, since geosynchronous satellites are very good for communication and broadcasting purposes, around 35% of all satellites are at the geosynchronous altitude. Besides the GEO and MAO, there's also the LAO. LAO satellites operate at altitudes between 200 and 2000 kilometers, requiring them to travel at high speeds around 28,000 kilometers per hour. These satellites are commonly used for Earth observation and communication. MAO satellites, on the other hand, are found at altitudes between 2000 and 35,000 kilometers. You would use MAO satellites for GPS, since their navigation calculations aren't as hard to do. Fun fact, Starlink satellites are the LAO to secure small time delays. The goal of Starlink is to provide Wi-Fi basically everywhere around the world. However, since they are so close to Earth, you would need a bunch of them to cover all of Earth. This made astronomers pretty angry, because their light polluted the entire sky. Let me know in the comments what you think about it. Anyways, all satellites will eventually, sadly, experience orbital decay. Orbital decay means that in satellites altitude will gradually decrease over time due to atmospheric drag. But since the atmosphere is denser the closer you go to Earth, LAO satellites have a lower lifespan, so their fuel runs out faster. You work at NASA, and you as well as your team need to secure the safety of a satellite. You try to find out the satellite's orbital velocity to ensure that it doesn't crash into Earth due to orbital decay. That's basically all the equations you would need to know for any satellite motion problem. And we picked this one. Yeah, I know that I showed you this one before. But that's life, man. Not everything is gonna be easy from the start. Sometimes you need to get out of your comfort zone and approach new things. 2 pi r tells us the circumference of a circle, aka the orbit of Earth, And the orbital period just tells us how long the satellite takes to finish one revolution. So it basically tells us the distance over the time. And velocity is all about that. Okay, let's say we already know the period and the radius. And as discussed before, we want to know the velocity of the satellite. First, we need to convert everything into SE units. After that, we need to add the radius of Earth, since r means the distance of the centers of both masses. And our r just tells us how far above the surface our satellite is. Then we can just plug in everything into the equation and get our final velocity. As a result, we get about 24,669.58 kilometers per hour, which is way less than the 28,000 kilometers per hour, so the satellite would just crash.